All right. So, take numero whatever the heck. Let's try 2.4, number 7. We're supposed to prove or provide a counterexample. Oh, that's not actually what it says. It says true or false. But these are infamously known as prove or provide counterexample. These are the bane of math students in general. Because if you're supposed to prove something, well, usually it's true, and then you can kind of construct a little bridge going from side A to side B, and if you have to go to side B and like back manipulate a little bit to get things to meet up in the middle, like you can usually manage that. The problem with prove or provide a counterexample is you don't know it's true, so you don't know that there exist these steps, so you just like walk out in a direction and then like get a little lost, but you don't really have any self-confidence about whether you can get to the end, so then you start to second guess yourself and it's really awful. These are terrible anxiety producing things. My strategy for them is to say, use your intuition as to whether or not this thing is probably true. You guys with me on that? So make a guess, even, and then attempt to either construct a counterexample or prove it based on that intuition, right? So if I think this thing is true, I'm going to spend a minute and try to make a proof for it. If the proof falls apart, I'm going to try to use the way the proof fell apart to make a counterexample. Does that make sense? If I'm trying to provide a counterexample and I keep running into a problem, I'm going to try to use that problem, like that thing that I can't get to work, I'm going to try to use that to prove it. You guys feel me on that? And oftentimes if I'm doing one of these problems and I'm really, really not sure and it's hard, I'm going to switch back and forth a few times. And this is why it's kind of important to like not madly erase things. Just like keep writing. Don't crumple shit up and throw it away until you're totally done, because you might realize that, oh, I tried something like that before and it kind of worked, so I'm going to go grab that piece from earlier. Does that kind of make sense? Don't rage delete things. All right, so let's kind of use that intuition here for, I don't know. Should we start at the top? Let's start at the top. So if columns 1 and 3 of B are the same, then so are columns 1 and 3 of AB. Does that feel true? Does that feel false? Where are you at with your kind of... Cody thinks that feels true. Is that what thumbs up means? Okay. So if this thing feels true, all right, so if columns 1 and 3 of B are the same, I guess that means that B looks like, well, it's got a first column, right? And then it's got a second column. And then it's got a third column, but the third column is the first column. And then it's got some more columns that I guess I don't know anything about. And then at the end, it's got some last column, right? You guys all with me on that?
Like some reason we have to add more columns to the end, or can we just specify that it's a 3-column matrix? Will it really make a difference?
Possibly, yes.
Okay.
In this case, what I'm trying to do is show them, like, I'm trying to prove this, which means I'm taking the most general case to hand.
Okay.
If I was trying to provide a counterexample, I'm surely not going to start building a 4x4 matrix unless I absolutely have to. Does that make sense? Like when you're building a counterexample, start with the smallest thing you can get. In this case, I'm trying to prove it, so I need the kind of most general case. And I guess I should probably have B4 as a vector here, ... n, because I don't want to give the impression that they're all B1, right? So in that case, then what's AB?
A times B1.
Good. It's A times the first column is the first column of this matrix, and then the next one is AB2. And then what's the third one? Well,
B1 again?
yeah, that'd normally be AB3, right? But I know that B3 is the same as B1, so this is going to be AB1 again. And then there's going to be the kind of more stuff. So there's going to be AB4 and going on to ABN. And so I can see that those are going to be the same. And so if I had to write a good response for this, right? I'd say true. The first column of AB is A times the column 1 of B, right? Obviously, I'm using some kind of shit shorthand here. You're going to want to write this out in like full human speak. And the third column of AB is A times column 3 of B, but because column 1 of B is column 3 of B, the first and third columns of AB are the same. And if I'm doing a really truly wonderful job, I maybe put a parenthetical after this one and cite where I found that. You guys with me on that? That's really just a column multiplication picture for matrices, so meh. Like I feel like you guys are comfortable knowing that fact. But if you're not sure that something's true or you dug something pretty obscure out, you really should cite it. Does that kind of make sense? Okay, how about rows? Is this true for rows? Does this feel true for rows? Why not, Jordan?
You're putting me on the spot here. I would need a second to think about it a little bit deeper.
Okay. So let me see. Do I know something that changes up rows when I multiply? I think that's kind of where I'm at, right? Like, okay, so I know that this changes columns, right? But it's just applied to each column. Whereas there's those damn elimination matrices.
That's what I was thinking of. Yeah, I'm with Jordan. I don't think it's true.
Okay, so let's work on providing a counterexample, right? So in order to kind of think about providing a counterexample, I need a matrix B, right, that has, I'm supposed to have row 1 and 3 of B are the same. So this goes to Jacob's earlier point of I'm going to start with as small a matrix as I can, right? So what's the smallest matrix I can make that has 3 rows?
Three by three or 3 by n?
3 by 1.
Good, 3 by 1. Right, so if I'm thinking about it as a function, right, the smallest square matrix I could make would be 3 by 3. There's a real inclination to like live in the place of square matrices. In this case, they didn't say anything about square, right? So I'm going to assume that I'm allowed to do this. Let's see. So a matrix that has some rows. I need row 1 and row 3 to be the same. So I'm going to do this, I guess. You guys with me on this? This is maybe not the simplest matrix I could exhibit with this property. What's the simplest matrix that I could make that had that was 3 by 1 with row 1 and row 3 the same?
1, 1, 1.
Yeah, maybe even dumber. You could use the 0 vector, right? I'm a little bit disinclined to pick the 0 vector here because I think that whatever I do to it, I'm going to get the 0 vector back.
Mm-hmm.
So that's probably not a great choice. You guys with me on that? Okay, so I got this thing. So let's see. I just need a matrix that, well, that leaves row 1 alone and changes row 3, right? So I'm going to think about using the E31 matrix, I guess. Does that make sense? Okay. How about I'm going to try... I'm going to try A is... I'm going to start with the identity. Right? And then I'm going to think about what happens when I apply this to the vector. Oops. So I'm going to get AB then, right? Is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. The identity matrix times 1, 2, 1. Okay, so if I do this, what do I get?
One, 2, 1.
Okay, did that work? Did I just find a counterexample? No, row 1 and row 3 are still the same, right? Okay, so this wasn't a good choice. Okay, so let me do something else. The simplest something else I can think of is to put something here. I'm going to put, I don't know, 1 here. Why did I pick that spot? Well, I picked that spot because I want to jam row 1 and row 3 together somehow. You guys see that? So I kind of used an elimination matrix as like inspiration here. So now when I actually do this multiplication, what do I get? Think if I
2 on the row 3.
Yeah, I get a 2 down here. Exactly. You guys with me on that? Okay. Rad. Is that a counterexample?
I believe it is, yes.
Yes. This is a counterexample because they said, right? If rows 1 and 3 of B are the same, so are rows 1 and 3 of AB. Well, here's a matrix B and a matrix A that don't have that property. So that is false. Here's why. And you really can just grab these as your answer. If you're doing a really good job, you provide the person who's looking at this calculation. And then maybe say something like, same. Not same. Like, yo, dude, notice. Those were the same. Then I did a thing. Now they're not. Bite me. All right. Let's see. So how about if rows 1 and 3 of A are the same, so are rows 1 and 3 of A, B, C. Huh. Hmm. I don't know. How do you approach this one? What do we need to start with? First, is it relevant that there's an A, B, C there?
I don't think so, because couldn't you just combine B and C to make a new matrix D?
Yeah. I'd probably be inclined to call it B, but, that's a little bit mathematically lazy. Yeah, I'd be inclined to say, like, I'm not sure that this matters at all. Like, this is just some new matrix. Always. Like, I know that for any matrix B and C, you get another matrix out of that multiplication. The one thing I'm not totally sure of is whether you can get any matrix that way. Like, is it true that any matrix D could be written as B times C? That might cause me a problem. You guys see that? It is actually true that that is the case, but it's not maybe an evidence.
Well, I mean, you could have an identity matrix and then multiply it by any other matrix. So,
And that's exactly how you'd prove it. Kick ass, Grayson. Right, you'd say, okay, well, screw it. Let C be the identity, then B can be the matrix I'm talking about, which is why I'm inclined to call it B. All right, so how do I go about figuring this out? Do you guys feel like this is true or false? What's the difference between this problem and the one before it? Like, how are those different?
you're working backward.
Yeah, this one's got the rows of the matrix I'm multiplying by, not the rows of the matrix. Sorry, that didn't make any sense. It's got the rows of the matrix on the left, not the rows of the matrix on the right. And somehow I feel like that's going to make this true. You guys feel me on that?
Yeah.
Okay, so let me see. I think maybe I'm going to approach this from a slightly different direction. Oops. That's useful. Okay, so it said rows 1 and 3 of the matrix A, right? So I'm going to think about my matrix A as a collection of row vectors, right? So it's going to be R1 like this, R2 like this. Oops, I did not give myself enough space here. R1 like that, and then R4, and then on down till I get to Rn or whatever. You guys with me on that? Okay, then I've got some matrix B. I guess B has columns, right? I'm going to need to figure out about columns here because it's the kind of pick up and drop on idea, right? You guys with me on that? Okay, so I'm going to have some columns. I'm going to call those B1, I guess. Out to BM, I guess. Not really sure how many of them there are. You guys see that? Would this make more sense if I just discarded the extras? Probably a little bit. Okay, let's discard the extras for a second, and then we'll go back and put them in. All right, so let me just slim this out to the case where I've got 3. So I've got row 1, row 2, row 3. So this is my matrix A. You guys with me on that? Okay, then I've got a matrix B. Matrix B has some columns in it, right? So I'm going to go like this. I'm just going to put a couple columns in here, kind of for me to think. I want to avoid the simple case where there's just one, but I'm just going to put in a couple. You guys on board with this? Okay, and then when I do this multiplication, I'm going to get a new matrix. Oh, I guess I started calling these C. I guess I should call them B. So when I do this multiplication, I'm going to get this matrix AB, right? And the IJ entry, ooh, that might get a... Let me scrap that for a second. That's going to get a little complicated. Let me just say this. So AB is a matrix, right? How big is this matrix going to be? How many rows you got here?
3.
Good. I've got 3 rows there. Do I know how long the rows are? No. I'm going to call it question mark because I'm just not sure what it is. Okay, over here, how many columns do you have?
2 and question mark rows.
Yep, and I know that the question marks have to be the same, right? In order to do this, in order for this multiplication to make sense, they're going to have to be the same. So if we're even writing down the symbol AB, right, then these things have to be the same. You guys with me on that? Okay, so I should get a 3 by 2 matrix, right? How do I get that 3 by 2 matrix? What goes right here? You pick up B1, right? You twist it sideways and you drop it onto R1. Right, so this first number is R1 dotted with B1. You guys feel me on that? What's this next number?
It's gonna be R1 dotted with B2.
Perfect. It is R1 dotted with B2. Oops, I wrote R2. It's R1 dotted with B2. And then what's in the next row?
R2 dotted with B1.
R2, B1.
Good. R2 dot B1 and R2 dot B2. And then the last row is going to be R3 dot B1 and R3 dot B2. You guys feel me on that? Okay, now what was special about my friggin' matrix that I had? What was special about my matrix A? I wrote it down as row 1, row 2, row 3, right? But what was supposed to be special about it?
Row 1 and 3 were the same.
Oh, yeah. So row 1 or row 3 is really supposed to be the same as row 1. So that means that these guys are supposed to be row 1. And then you guys see this? That vector there and this vector here are the same. Go ahead, check them.
So for like B, since it was false, could we not use a technique like this to prove it's false?
Oh, yeah, you could certainly prove it's false.
But we would also need to provide an actual example.
So the thing about proving it's false is that the method by which to prove that a claim is false, like the easiest one, is just to provide one thing that doesn't work.
Yeah, but what if we don't know off the bat whether it's true or false? Like we knew for B that it was probably going to be false, but if we had no idea and we did a proof like this, would this be enough?
Unfortunately, not, because if you do a proof like this, or if you construct something like this, what you're going to get is that, well, they don't necessarily have to be the same, but that kind of incomplete thought isn't going to prove that they are, isn't going to prove that they can be different. Does that make sense?
Yeah, but it's
Probably.
asking if it's the same. So if you show that it doesn't have to be the same, isn't that the same as proving that it's not always the same?
You should provide a counterexample, because it's possible, right, that there's some accident that you just haven't completed the proof. Does that make sense?
But then couldn't you make that argument for C and A as well?
In this case, the proofs are complete, right? They flow from, if the columns are the same in the first matrix, then the columns must be the same in the second matrix. Whereas the idea of like, okay, could these be different, is a little bit harder to nail down, basically. Does that make sense? Like, you could certainly use this as inspiration. If you drew this up, right, you'd say, okay, so these kind of results don't necessarily have to be the same because one of them is constructed out of R1 and the other one's constructed out of R3, and those could be different. I guess I'm saying that I wouldn't find that persuasive, but I probably would. Yeah, you could do that. I would like to see a counterexample, though.
Okay, because the only difference would be plugging in values for your R's and B's. So I don't really see what difference it would make.
Yeah, that's true. Okay. Most people are more certainly it's more persuasive to provide an actual example. So the kind of classic philosophy of science thing is this nonsense about all ravens are black. This statement is false. All ravens are not black. Because there exists a single raven that is not black. If you want to demonstrate this, the easiest way to do it is to go find a white raven. Does that make sense?
Yeah, I guess.
All right. And then how about for D? D says, give a specific example when it's false. So what do you need here? Well, wait. Is this true? Is this false? Oh, God. I need my intuition again, and I lost it. So what is it? What's the difference between AB squared and A squared B squared? What should AB squared be?
AB times AB.
Good. So I'm just going to do D here in the margin because it's not very big. So AB squared should equal AB, right? And this is actually a good, this is maybe a good illustration of what Jacob and I are talking about. So if I've found that AB squared is AB, and then there's a claim that should actually equal A squared B squared, well, does it? Maybe. It certainly is true with numbers. Do you guys remember that I warned you about this with matrices? I do kind of like having all this stuff right here because I can just call back. Oops, that's... I could call back if I can find things.
You have the receipts.
I have the receipts for the things that I've said. Yeah. So remember that a matrix A times B, right, is a function composition. Right? So AB might not be BA because they're functions. And so in this case, I'm looking at this set of 4 function compositions, right? And I feel like the order probably matters enough in functions. So I would be pretty inclined to look at this thing and say, no. Because AB isn't always BA. So this is the kind of like general proof strategy that Jacob's saying is persuasive. This should be persuasive. You should now be persuaded that AB quantity squared is not A squared B squared here. However, I feel like I probably need an example for this. You guys with me on that? Okay, so an example? Where am I going to come up with an example? I just need a couple of matrices that don't commute, right?
Yeah, you would need an A matrix and a B matrix that does not equal the B matrix, right?
Yeah, so I need A, B so that A and B, so A, B isn't BA, right? And even then I have maybe, like, I'm not totally sure that would work, which is why I really should have to provide a counterexample here, because it is possible that there's like some funny manipulation that has to happen, right? So my claim for these would be, let's see. Oh, hell, I don't know. I guess I'm kind of inclined to use this matrix for A. And I don't know, something else for B. Now I've got maybe a little work to do on this, right? You guys with me on that? Okay, so I just need to calculate these two things and show they're different, right? So a matrix calculator would be an easy way to do that. The other thing you could notice is that if you square the matrix A, you get the matrix A again. You guys see that?
Yes.
Okay. How much calculator stuff have you guys been doing versus how much by hand stuff? It's all by hand.
It's all by hand, but I can't find how to do it on my calculator. Like, I found something that multiplies a matrix by a vector, but vector calculator or matrices I haven't been able to figure out.
Okay. So I'm gonna showcase a little tool later. For right now, let's go just get a matrix calculator off the internet. I'm just Googling the words matrix multiplication calculator. Whoops, I meant to make that only part of the window. Okay, so I want to set a couple matrices. So I want them to be both 2 by 2. Oh, actually, that gives me an easy cheat way to do this. Should we just do this the easy way? No, let's not. Never mind. Sorry. So my matrix I want a 1 here. Fill empty cells with 0. 1, 2, 3, 4. Calculate. Okay, so in my margin here, I found that 1, 0, 0, 0 times 1, 2, 3, 4 gave me 1, 2, 0, 0. And now I just want to go back and oops. So now I want to set those matrices in the other order and just double check that I actually have 2 matrices that don't commute. Okay, cool. You guys see these matrices don't commute? Oops. 1, 0, 3, 0. Okay, so now I have my 2 matrices that don't commute. And now I think, all right, so let's see. I need to know what AB is, right? You guys see that? This is my matrix A, this is my matrix B. This is my matrix B, this is my matrix A. So this is the matrix AB. Are you on board with that? Okay, so I'm going to take this thing and multiply it by itself. So that thing is 1, 2, and 1, 2. That was weird. Did I miss a number there? That feels real weird. You guys all see why I'm skeptical about this? I found a matrix that when I square it, it gives itself. Huh. Okay. Checks out, I guess. So I found out that this is the matrix 1, 2, 0, 0. Uh-oh. This one probably isn't going to work. Cool. Okay, so let's see. Now I need a squared. So a is this one. Oops, and a is still this one. Okay, so I'm taking a and squaring it. That's giving me, so I got a squared is just 1, 0, 0, 0. And now I need b squared. Okay, so that was the matrix 1, 2, 3, 4 by 1, 2, 3, 4. Oh, that's wild. That's way different. Maybe this will work. So I got my matrix B squared was 7, 10, 15, 22. You guys all on board here? Okay, and then finally, what do I need? What's my last calculation I need to run here? My little calculator.
A squared and B squared.
Yep, so I need to take these 2 matrices, multiply them together. So I got A squared is just A, but B squared is 7, 10, 15, 22. And we hit calculate, and we get 7, 10, 0, 0. So I got A squared B squared is 7, 10, 0, 0. So this was all part D. Continued, I guess. Okay, so what's my counterexample then? These two back up here. This matrix A is a kind of a special thing that we're going to talk about a little bit later. Do you guys recognize what A does to a vector?
Gets rid of the second row.
Good. Yeah, it just dumps the y coordinate, right? That's a map from R2 to R2, yeah? So that's like when you take a vector in R2 and you just forget the y coordinate, what does that feel like? You've got a vector in R2, right? X-axis?
Turning like a man. I just blanked. I had it in my head.
So I've got kind of R2 like this, right? And then if I've got some vectors, if I apply this map, I just set the y coordinate to 0, right? So that just kind of smashes them down this way. Right, so that first one, I shouldn't use the arrows that way. So this first one turns into this guy, right? Because the y coordinate just gets set to 0. This one becomes that guy. And this third one becomes that guy. So it's just smashing things
No more
vertically.
slope.
It's this is what's called a projection matrix. It just takes the entire R2 space and just flattens it onto the x-axis. Does it make sense why you'd want to do that? Okay, how about if it was 3-dimensional and you wanted to project it onto 2-dimensional space? Would that be a useful thing? Why would that be useful?
You could get rid of the Z.
Yeah, I mean, or at least you could get rid of something, right? You could get rid of one coordinate. Do you guys ever have an occasion where you see like something that's supposed to be 3-dimensional, but then it's like rendered on a 2-dimensional surface?
Mm-hmm.
Really? When does that happen?
I don't know, video games.
Yeah, basically all the time. Like, right? Anytime you're looking at something on a computer screen, a lot of the time it's a 3-dimensional object rendered in 2D. And the way that's done is with this kind of projection operation. Right? If you think about your character in your video game's head, right? It's like a plane. And then the entire game is being projected onto the plane that's perpendicular to where you're looking. And then you're just seeing a piece of that. It's actually a really cool thing. But this is why linear algebra is important for people who want to do video game physics. All right, so good. That took forever. Any questions on that whole process? That was a lot.